Hello, this is Jeff Hamrick at the University of San Francisco's Financial Analysis program, and I'm going to talk about implementing what's called a partial f-test or a restricted f-test in Stata for a few minutes. What I've got here is our body fat percentage data set that we've used to illustrate a number of concepts related to multiple linear regression. And what I've done is I've regressed body fat percentage against age, weight, abdominal circumference, ankle circumference, and circumference of the biceps. And as you might imagine, several of these variables are very statistically significant in this model, which has a reasonably large R squared. Namely, weight is highly statistically significant, as is abdomen. Bicep circumference is marginally significant, and the other two variables, age and ankle, do not appear to be statistically significant at all. You might then be tempted to delete age and ankle from the model, but it's important to understand that that's a joint decision. That is, you're making a decision to eliminate age and ankle at the exact same time. And what you basically see in this table, by looking at each row one at a time, is the marginal test on each coefficient in each row. They ignore the effects of other variables, except in the sense that the coefficients have been fitted at the same time. So, for example, this p-value is related to the statistical significance of age, and that's a different matter than the concept of deleting age and ankle at the same time. To manage this situation, you need to run what's called a partial f-test, and in Stata this is actually fairly easy. So if I add, after I've run a regression, the command test, and I use both age and ankle, what this command in Stata does is it tests whether or not at the same time the coefficient for age is equal to 0 and the coefficient for ankle is equal to 0. Okay? And so when we execute this test in Stata, we get a very small f statistic and therefore a very large p-value. Therefore, we cannot reject the null hypothesis that at the same time age is equal to 0 and the coefficient of ankle is equal to 0. So we probably would be justified in deleting age and ankle from this model. Now, I'll completely acknowledge that the decision related to this test is different, is the same as what we would have accomplished by using just the t-test on the coefficient for ankle and just the t-test on the coefficient for age. But that is not always going to be the case. So where do these degrees of freedom come from for this f statistic right here? It's fairly easy to see. The 2 here comes from the total number of restrictions we induce in the f-test, because we have 2 separate equations here in which we test null hypotheses involving these variables, their coefficients being equal to 0. That's why we've got 2 in the numerator here. And the denominator is clearly much more related to sample size. So our original sample size was 252. We had 1, 2, 3, 4, 5, 6 fitted coefficients initially in the original model. So 252 minus 6 is going to be 246. So that's where the denominator degrees of freedom come from right here. Okay, so this is the partial f-test as computed in Stata, and I gave you a version of this partial f-test to conduct by hand in class, but Stata can run a much larger collection of partial f-test in it can run a much larger collection of f-test. For example, I can test whether or not the sum of the coefficients for weight and abdomen, is that statistically distinguishable from 0.5. Now when I add these coefficients right here, I see that it's definitely above 0.5, but maybe in the sense of this restriction, the sum of those two coefficients is not statistically distinguishable from 0.5. Well, when you execute this test in Stata, notice that there's a couple of differences. We have one restriction here, that is one equation, so we have 1 degree of freedom in the numerator of this f statistic, and we have the same number of degrees of freedom in the denominator. Now this f statistic is very large, and the associated p-value is very small, so that means we can definitely reject the null hypothesis that the sum of weight and abdomen is equal to 0.5. And in some sense that makes sense. If I take for example, the smallest possible value here in the 95% confidence interval for abdomen, 0.81, and I also take the smallest possible value for weight in this confidence interval. The sum of those two is above 0.5, so we kind of would think, just using the data from the regression output, the information from the regression output, we would think that no, the sum of these two coefficients is not equal to 0.5. But what we really need to do that is what's called a restricted F-test, or a partial F-test, using this particular restriction, namely that weight plus abdomen is equal to 0.5. So Stata can do all sorts of restrictions, the products of several variables, whether or not one variable is equal to the other variable, and so on and so forth. So the proper way to make to resolve joint hypotheses about coefficients is with a partial F-test of some sort, not by somehow kind of gluing together individual inferences using the student t-tests that have implicitly been run in this table right here. So this is the partial F-test or restricted F-test in Stata. Let me know if you have any questions.